little bit before the break, there is a connection between, there is a calculus connection between position, velocity, and acceleration. And the short answer is it's the derivative. Now, you're in calculus now, so everything kind of gets interpreted through slope. You might hear me say to put on your slope glasses. If you forgot your slope glasses, you can borrow your friends, but when you put on your slope glasses, you're kind of like always thinking about slope. You're seeing slope, and of course, what that really means is the slope of the tangent, because you've grown, you now know that a curved line can have slope. So put on your slope glasses. And by the way, you probably don't need to write anything down yet. We're going to do an actual problem, and then probably you can write something down. But if you put on your slope glasses and you think about this position graph, well, maybe we should just back up a second. I want to make sure that you realize that I'm sort of talking the same talk that a physics teacher would. And if you haven't had physics, you can still understand this, because basically this is the position of like a projected object, and even more simply, just a vertical motion. If I throw something up in the air and it comes back down, we call that simple vertical motion. And this graph is trying to display the height of the object. So we know it goes up, it reaches a maximum, and then it comes back down. Again, pretty basic stuff. But when you interpret this position graph as through sort of a slope perspective, you start to see some other things. Like, take a look at the slope maybe at the beginning. The slope at the beginning, well, it would be pretty steep. Okay, it would be large. Versus the slope in the middle, which would actually be a slope of 0. What is equal to 0 when you project an object, when you go through vertical motion? What is equal to 0 when you're at the top? Velocity. Okay, and again, the simple connection is the slope of this is equal to this. Kind of like Colton said, the derivative of this is equal to this. So when we use our slope classes and we see a slope of 0, we actually see a velocity of 0 also. Okay, we see a velocity of 0. So, big velocity, steep velocity. At the end of the graph, we also have a steep velocity, but it's negative. And so, again, especially to my physics kids, but for all of you, when you think about an object's velocity coming back to you, we know that that's called negative velocity when it's coming back to you. Just like this slope is negative when we're at the end of the motion. All I'm simply trying to show you is that the things that you know about velocity are also true about the slope of this graph, because they're the same. Okay, now let's actually put some numbers to this. Like, hold on a second. Let's get some notation, and maybe this notation is the same that you would have seen in physics. If it happens to be different, it's okay. It's the notation we're going to use to describe position, velocity, and acceleration. Basically, S of t, V of t, and the A of t. S of t will be our position function, and then V of t will be velocity, and A of t will be acceleration. Not too hard of stuff, but just so we're all talking the same way. Okay, and then it's not just some facts, it's actually kind of the fact. It's like the main thing. And let's just reveal it now in notation form, that S prime of t is equal to V of t. In other words, the derivative of position is equal to velocity. The derivative of position is equal to velocity. Now be careful, this might be like this part in the lesson where you sort of either decide to sign on and kind of like, pay attention. It might be the part where you kind of like zone out because it's getting a little like physics. Okay, but physics doesn't have to be a bad thing. I actually kind of enjoyed physics when I finally got to take it in college with calculus. Okay, when you were able to use calculus in a physics class, a lot of kids say, geez, it makes sense. Okay, remember, I'm only going to be doing like basic physics stuff here because I just want you to see the connection. So we're not going to get into a lot of the complicated stuff that you would have done or did upstairs. And that kind of makes it a little easier too. Okay, so the derivative of position is equal to velocity, which maybe you would also say that the slope of position is equal to velocity. Okay, let's have like a velocity equation, shall we? Let's have an actual velocity equation. S of t. Oh, sorry. I didn't mean velocity equation. I meant a position equation. Let's have an actual position equation. S of t equals 128t minus 16t squared. So again, here's a position equation. Now, I have to admit to you that if I kind of think back to when I was trying to learn physics, whether it was high school physics or college, sometimes just what do you mean position? Okay, what do you mean position? And in the case of this problem, there would be some other text that would probably be written here that would say that this is the position of a rock, we'll say a rock, that was thrown up in the air. I had a racquetball a second ago, but let's say it's a rock that's basically just thrown up. And so this equation with a little different window so that we can see 10 seconds. Again, I'm going 0 to 10 because if I throw a rock up in the air, I mean, it's going to be quite a chuck for it to go much more than 10 seconds. And then maybe I'm really strong or whatever launched it's really strong, so we'll go up to 400 feet. I don't have all that extra stuff here, but it's in feet. And again, that's quite a shot. But we get a graph that basically looks like the one that we started with here. Okay, so that graph displays the position at different times. Okay, now, so that we can get a little more specific here, we could say that this time is obviously 0, but now that we have a graph that we can look at, we could see that it appears to last 8 seconds. So we can get some actual times, and then this one in the middle by basic observation or by some simple physics we know is halfway, so that's t equals 4. Now, the whole idea is that those 3 times have some special velocities. So let's check them out. What I want to do is just make some velocity observations with you. Now, if we're going to make some velocity observations, then we need a velocity equation. And this is supposed to be kind of the fun part. This is the part where we say we can use derivatives. Look, Mom, I can do the derivative. I can do the derivative of position, and all of a sudden I get the velocity equation. Honestly, some of those, let's make sure we understand the derivative here. Don't forget the derivative of 128t. That would be like taking the number 1 and just bringing it down. Of course, when you subtract from the number 1, you get 0. So that's why we just write down 128. And then bring your 2 down and get 32. Don't forget to subtract. Now you get t to the first. So pretty easy derivative. Nice job on the quizzes too. I'm really impressed with how much you guys picked up on in just, one section. Okay, now the cool thing is that derivative is the velocity equation. So let's make some velocity observations. I was just mentioning over here that at t equals 0, we should have like the fastest velocity. So let's find out. Let's find out what the velocity is at 0. What I hope you see me doing here is I'm plugging in 0. Oh, that seems like something we've done before. Like plug in to a derivative. You did it on the quiz. Almost all of you did it correctly. So when you plug into the derivative, you get the slope. But in this case, we get the velocity. Okay, now, like I said, I didn't put all this extra labels, but this would be in feet per second. Okay, because again, this problem is in feet and seconds. How about the velocity over here at sort of the end of the motion? Now, before we do this, especially again to my physics kids, which appeared to be just about all of you, you should be able to predict this velocity, okay? Because you know that the velocity from release compared to the velocity when it comes back, okay? I don't want to say it's the same, but you should be able to predict. So let's see what happens. See what happens. Plug in 8. And if you would want to put that in a calculator, you can, or if you just want to take the teacher's word for it, but it should be confirming what you've learned, and that is, of course, that the velocity, it's not the same, but it's going to be the opposite, which, again, it's negative. It makes sense. The object's coming back. We know that negative velocity is when I come back towards the starting point. That's good. How about the point up here, which you guys will come to know is sometimes the most critical point when the slope is equal to 0? Oh, you mean when the velocity is equal to 0? And indeed, when you plug in 4 and you get 4 32s, that's going to be 128 minus 128. Okay, now, what I'm basically trying to show you here is I'm not making this stuff up. Not that I would think you think I am, but everything we said about the slope of this graph is true about its velocity. Okay, because again, that's kind of your main connection. That's your main fact. Well, a good physics lesson wouldn't be good unless we had the graph of velocity. The graph of velocity. Remember making those graphs of position and then velocity? And then, of course, there's that last one. But what about the graph of velocity? Okay, now, what you'll learn this year is that we can make these graphs based completely on slope. We can make these graphs based completely on slope. If you think about it, we have that information right now. We have the slope at 0. It was equal to 128. If I'm going to make a graph of that, then I'm going to put a point at 128. Of course, matching up with 0. And then I have a slope of 0, or a velocity of 0 at 4. Okay, so I'm putting a point at 4, 0. I guess we should get a little more exact and call this 0.28, 0.128. Okay, and then there's one more point that I have. Of course, it was the one when I'm at 8, I have a negative 128. Now, maybe that looks familiar, maybe it brings back good or bad memories, but that is the velocity graph. That is the velocity graph of this position graph. But you know, math really exists so that you guys can go upstairs and apply it. I hope that you're realizing that if you're taking more science classes. So what we're doing downstairs is just so you can go upstairs and apply it. So I have an equation, I can graph it. And if you graph that equation, this shouldn't be that earth-shattering, because what I'm graphing right now is just a little y equals mx plus b. I'm just graphing a little straight line. Oh, you mean like the same straight line that we drew right here? Yeah, the same one. Have to mess around with the window a little bit so that we can see it. How about mess around with it the correct way? Oh. Okay, but of course the graph of 128 minus 32 is going to end up being that straight line. Okay, so there's your velocity graph. Position, velocity, and of course the third one is acceleration. Position, velocity, and acceleration. Now, acceleration is just the next derivative. Basically, the derivative of velocity is going to come out to be your acceleration. So again, it's just the next derivative. Now, of course, acceleration, I shouldn't say of course, but acceleration is that force that's acting on your object. Okay, it's that force that's acting on your object, causing it to change in that certain way. But let's find the acceleration. Let's find the acceleration of our original position equation. Okay, now we already have a derivative. We already have the velocity. So we just need to do the next derivative. So if I do the derivative of velocity, I'll take a look at this. Maybe I should label this a little better here. We're working on the acceleration. Take a look at this. We're going to do the derivative of 128 minus 32t. The derivative of 128, well, that just becomes 0. The derivative of minus 32t is minus 32. So our acceleration is a constant. Our acceleration is a constant. What constant is constantly acting on an object that goes up in the air and comes back down? What constant it is. Now, you're used to seeing as 9.8, right? 9.8 meters per second squared. Just wanted to do it a little differently today. But that's just in feet per second squared. So this is gravity in feet per second squared. It's your acceleration due to gravity. It's your gravity force. It's your gravity constant. And again, part of today's lesson is just to realize, oh my gosh, okay, that is brought to you by derivatives. That's brought to you by derivatives. So again, it's the same acceleration as I go through the entire motion. Because as Delaney said, it's gravity. Okay, now, if you were going to graph this, it's not really that fun of a graph, but you still could graph it. Because you're just going to be graphing a horizontal line. You're just going to be graphing a horizontal line. Now, as we go deeper in calculus together, it's going to be a fun adventure. What you're really going to realize is that we're just talking about slopes. Okay, even back in like Algebra 1, when you started talking about slopes, you were getting into calculus. But just want you to notice something, because the sooner you start to notice these things, the more you can go deeper with me. The position equation was a quadratic. It was of a x squared form. It's a curvy line. But each time you do the derivative, look what's happening to the degree of your function. Okay, because it was a degree 2, now it's a degree 1. It's not a curvy line anymore. Okay, it's a straight line, it's a diagonal line. But as you continue to do the derivative, your degree, your exponent, keeps going down until we finally get to a constant. Okay, and then of course that line, it's still a straight line, but it's even less dynamic. It's horizontal. What about the next derivative? The next one after acceleration. By chance, anybody talked about it in like a physics class? It's position velocity, acceleration. Don't be a jerk. Don't be a jerk. Okay, and there's little t-shirts you can make up. Don't be the third derivative. It's okay to be the first derivative, then your velocity. The second derivative, your acceleration, but don't be a third derivative. You'd be a jerk. Okay, now what's jerk? I'm not the science teacher, but it's like the next force. Okay, it's almost like acceleration on steroids, kind of like what jerk would seem like, kind of that acting force on that acceleration. The jerk for this would be 0, so there is no jerk. But again, I'm being honest with you, I don't have like a big example of how we use that. It'd be something you could talk about more in your physics class. Okay, now that was meant to be an introduction, but also showing you concepts that we will apply tomorrow.